Okay, so before I begin, I'd like to see if there are any questions that people have on the material or on the homework or anything like that. I know that we are doing some stuff that's a little more abstract with the Wronskians, so I just wanted to make sure that if anyone has any questions, that I'm available. Of course, I have office hours after class today, so I'd be happy to chat over some of these topics if you'd like. I've also posted 2 new homeworks. Sorry, once again, that was a little late, but I've posted homeworks associated to section 3.1 and 3.2 yesterday, and today we'll finish 3.2 and then move on to 3.3. As one other remark or note before we get started, I just want to say that I have graded the first of the 5 problems on the exam, and most people did quite well. I anticipate that I'll have finished the grading by the end of the weekend, so I think you should have your grades up by Monday. So yeah, that's kind of the schedule that I'm on for the testing. Okay. So let's see, where were we? To kind of recap what we've discussed in section 3.2 thus far. 3.2 is we're discussing some generalities on order 2 linear differential equations, ODE. So one particular point that we have is that we have a, what I'll put as strong, I can explain what I mean by this, but a strong form of the existence and uniqueness of solutions. To IVPs. And what I mean by this strong here is that just from looking at the differential equation and the initial data, you can immediately tell what the maximum interval on which your solution could be defined. And then the theorem tells you that you can actually find a solution that is defined on that entire interval. So you can kind of extend the solution to the largest possible domain that you can read off. So this is different from existence and uniqueness in the nonlinear case. Then when we were discussing, so we discuss general families or general solutions or families of solutions. And in particular, what we discussed in this topic was we were trying to find, like if you're given a family of solutions, something like C1, Y1 plus C2, Y2. I can think of this as a family of solutions to a differential equation if Y1 is a solution and Y2 is a solution. And the question is, can we find y is equal to C1Y1 plus C2Y2 satisfying an IVP? So this is kind of a fuzzy question, but can someone remind me more or less what the answer is going to be?
Yeah, we can, as long as Y1 and Y2 are linearly independent.
Exactly. The answer is yes. Yes, as long as Y1 and Y2 are linearly independent in a suitable way. And what the suitable way here is I need to make vectors out of y1 and y2 by considering essentially their Wronskian, which contains the data of the function and the first derivative of the function. So if the Wronskian of y1 and y2 is not the zero function, which is equal to det of y1, y2, y1 prime, y2 prime, is not zero, not the zero function. So it could be zero in some places, but as long as it's not equal to zero uniformly, then y1 and y2 form a fundamental system of solutions. Or in other words, this family that I've written up here really is the general solution, and any solution to any IVP associated to the differential equation can be expressed as C1y1 plus C2y2. Okay, so those were the things that we really discussed a lot yesterday. What do I want to do next? I want to remark, or what I want to do is an exercise. Oh, not an exercise yet, sorry, I'm a little, yes, here's what I want to do. So, question, can we always find solutions y1 and y2 such that their Wronskian of y1 and y2 is not uniformly zero? Right? This is like kind of the last thing that we could possibly ask for. We have a very clear understanding of when we get a nice family of solutions. The last question is, can we always find solutions y1 and y2 such that their Wronskian is non-zero, so that y1 and y2 form a fundamental system of solutions? And here the answer is yes. And it's once again going to rely on the existence and uniqueness theorems. So the idea is very simple. So we're looking for solutions to a differential equation. What I'll write is L of y being equal to 0. So L represents my differential equation, and so I'm looking for functions y such that L of y is equal to 0. These are solutions to my differential equation. And in particular, L of y here is the same thing as y double prime plus p of t times y prime plus q of t times y. Right, so I'm once again back in the setting where I'm trying to think about linear second order differential equations. Okay, so what we need to do is we need to choose an interval I on which p of t and q of t are not equal to, or are continuous. What am I guaranteed on intervals I where p of t and q of t are continuous?
Existence?
Yes, I get existence and uniqueness on this interval. So existence plus uniqueness theorem guarantees me existence, uniqueness of solutions to IVPs on this interval. So now all I have to do is explicitly choose some initial data such that the Wronskian at t0 will not be 0. So I pick t0 inside this interval I, on which p of t and q of t are continuous. And then let's see, I should move on to a new paper. Then I essentially ask for solutions with the following initial data. Then get solutions with the following initial data. I'm going to ask that y1 of t0 is equal to 1, and y1 prime of t0 is equal to 0. And I'm going to ask for a solution on this interval with initial data y2 of t0 is equal to 0, and y2 prime of t0 is equal to 1. By the existence and uniqueness theorem, I'm on an interval I on which p of t and q of t are both continuous. So the existence and uniqueness theorem tells me all I have to do is specify some initial data, and there must exist some y1 such that, so exists unique y1 such that L of y1 is equal to 0, and y1 satisfies this initial data. And it's the same thing for y2. There must exist a unique y2 such that L of y2 is equal to 0, and y2 satisfies initial data. So you see, maybe you're slowly starting to see how powerful the existence and uniqueness theorem is. Because I'm trying to produce a basis, or I'm trying to produce a system of fundamental solutions. What I've done here is I've found some interval on which my functions are continuous. I've picked some point, and then I've just demanded that the Wronskian of these solutions is non-zero at this point, right? What's the Wronskian? What is now W of y1, y2 evaluated at t0?
One.
Yeah, this is just equal to det of 1, 1, 0, 0, as I've written here, which is equal to 1. So I have produced, in some magical way, via the existence and uniqueness theorems, solutions which satisfy the fact that their Wronskian is not 0 at t0. Thus, y1 and y2 are a fundamental system. So maybe all of this business with the Wronskian has seemed a little arcane, or like I'm reproving things a bunch of times, or I'm going over the same concept again and again. And it's really true. I've been discussing the concepts of linear independence, the Wronskian, and existence and uniqueness for like 2 hours of class time at this point, and just using them in slightly different combinations. But the main thrust essentially is that we can find general solutions to second-order linear differential equations. Maybe not explicitly, but by the existence and uniqueness theorem, we can produce y1 and y2 satisfying this initial data, such that the Wronskian of these two solutions at a certain time t0 is not equal to 0. And as we showed yesterday, this is enough for y1 and y2 to be a fundamental system. So every solution to this differential equation looks like c1 y1 plus c2 y2 for some choices of constants. How are we doing on this? Have you gotten back into the memory of this Wronskian business?
Yeah, that's good.
Okay. So what I'd like to do is I'd like to now have you do an exercise which points out kind of an interesting feature. Let me write it out in this fashion. So as an exercise, and you've already done this, so this should be pretty easy or quick. So find a fundamental set of solutions to y double prime minus y is equal to 0. And this was the very first example that we did in this chapter. So what are two solutions that we found to this differential equation?
E to the t, e to the negative t.
Right, exactly. Via characteristic equation, we see that e to the t and e to the negative t are solutions. Last time you checked that if the roots of the characteristic polynomial are distinct, then the Wronskian is what? Is it 0? This was like our last exercise last time. Well, okay, why don't we just compute the Wronskian of these functions? I know that this is kind of repetitive, but that's fine. Do we agree that this is the form of the matrix that we would get from these two solutions?
Yeah.
Yeah.
So what's the determinant of this matrix equal to?
Would it be -2?
Mm-hmm. The solution here is -2 because e to the t times e to the negative t, or negative e to the negative t, will give you a -1. So you get a -1 minus, and then e to the negative t times e to the t is going to be 1. So this is just going to give us -2. The Wronskian is not 0, so what does that mean?
That we have a fundamental set of solutions with just
Exactly.
arbitrary constants.
Exactly. So C1, so y is equal to C1 e to the t plus C2 e to the negative t is the general family, or is the family of solutions. Okay, now what I'd like to do is, so in a certain sense, we can think of et and e to the negative t as a basis. Now what I'd like to do is the following. Pick t0 to be equal to 0. What I would now like for you to do is find y1 and y2 such that y1 of t0 is equal to 1, y1 prime of t0 is equal to 0, and y2 of t0 is equal to 0, and y2 prime of t0 is equal to 1. for the same differential equation. We're not changing the differential equation that we're using. So just to get us started a little bit, if we want to find y1, then essentially we're asking for c1 e to the 0 plus c2 e to the negative 0 being equal to 1, and c1 of e to the 0 minus c2 of e to the negative 0 being equal to 0, right? Do you agree?
Yeah.
Right? This is just translating from our general solution, which is y is equal to c1 e to the t plus c2 e to the t, negative t. I'm evaluating this at t is equal to 0, and then I'm just seeing what are the conditions that I have to satisfy. So what are c1 and c2 for y1?
Wait, why does the second equation equal 0?
Because I've demanded it in my initial condition. So I'm essentially solving an initial value problem. I know that my general solution is c1 e to the t plus c2 e to the negative t. And now I'm looking for the specific numbers c1 and c2 such that when I evaluate this at 0, I get 1. And when I evaluate the derivative of this at t is equal to 0, I get 0. So here is the equation, like, if y is this, then the derivative, y prime, is equal to c1 e to the t minus c2 e to the negative t, right? And so just this condition is saying, when I plug in 0 to this equation, I should get 0.
Okay.
Now is that a little more clear why this looks how it
Yes,
looks?
thank you.
So what are c1 and c2 that satisfy this differential equation?
Is it just one?
Not quite. So to simplify this a little further, this is saying c1 plus c2 is equal to 1, and c1 minus c2 is equal to 0.
Half.
Yeah, so it'll be 1/2, right? We can see by adding together this linear system that 2c1 will be equal to 1. So c1 is equal to 1/2. 1/2 e to the t. And then c2 has to be negative 1/2, so that c2 also has to be 1/2, so that they both add to 1 and they subtract to 0. So plus 1/2 e to the negative t. There's a name for this function. Does anyone know what the name for this function is? It's okay. It's not so common. This is called hyperbolic cosine. So this is also equal to what's written as, cos h. So this h is for hyperbolic cosine of t. Okay. And then second of all, let's find y2, where now I demand that y2 satisfies these conditions. So why don't you find y2 for me? or this is actually 1/2 times cosh t, I think. No, this is just cosh t. So it's a very similar linear system.
A negative half and positive half.
Yeah, exactly. It'll be a negative 1/2 and a positive 1/2. So this is going to be equal to 1/2 e to the t minus 1/2 e to the negative t, right? Is that what y'all got?
Yeah.
We can check that when I plug in t is equal to 0 to this equation, I get 0. When I take a derivative of this equation, that'll essentially just flip it to 1/2 e to the t plus 1/2 e to the t. And then when I plug in 0 to that, I'll get 1. Okay, so this is also called hyperbolic sine. This is also called sinh of t. Okay, and all that I want to really note here is that another fundamental system of solutions to y double prime, what was our original equation? Y double prime minus y is equal to 0 is given by y is equal to c1 cosh of t plus c2 sinh of t, right? We know that these two solutions, y1 and y2, form a fundamental system of solutions. Why do we know that? Why am I sure that y1 and y2 are a fundamental set of solutions?
Because we set the initial values such that they would be.
Exactly. I built these whole functions around the fact that the Wronskian of these two functions at time t is equal to 0 is the determinant of this matrix, namely 1. So we constructed these functions so that the Wronskian w of y1, y2 evaluated at 0 is equal to 1. So they're guaranteed to be linearly independent in our suitable sense, which means the Wronskian doesn't vanish.
Does that mean we didn't have uniqueness?
We certainly have uniqueness. We have existence and uniqueness, but the point is there are many different ways of writing the family. So if you work out, what do I want to say here? So essentially these two are the same family. C1 e to the t plus C2 e to the negative t versus C1 cosh of t plus C2 sinh of t. The point is, when you write your family this way, and you pick some initial value or initial data, there's going to be some unique function that can be written in this way for some chosen constant C1 and C2. That same function can also be written this way for some different constants C1 and C2 here. So essentially what this really is this should be thought of as a change of basis. So in other words, the E1, like when I think of a change of basis, maybe one thing that I think of is a very nice basis of R2 is 1, 0, and then 0, 1, right? This is one basis. And then another basis of R2 is something that looks like this. Say 1, 1, and 1, -1. So the point is, given any point out here, there's always a unique way to express it in terms of some constants multiplying by these vectors. But since these are linearly independent, there's also a way of expressing this vector as some linear combination for some different coefficients in terms of these vectors. But this vector is still the same. There's still a unique vector that's, you know, this vector is still unique. It's just being expressed or written in terms of two different bases, so to speak. Does this kind of make sense or no?
Yeah.
Maybe a good here's a good exercise actually. Let's do one more exercise to see what's going on. Example. So if we have the family C1 e to the t plus C2 e to the negative t, then let's examine e to the t. This is a member of this family. Right? And in particular, we can find some initial data that e to the t must uniquely satisfy. In particular, this satisfies y of 0 is equal to 1 and y prime of 0 is equal to 1. Right? So this initial data, so I've got the initial data of y double prime minus y is equal to 0 and y of 0 is equal to 1, y prime of 0 is equal to 1. Do you agree that this is a member of this family, so it satisfies this differential equation and it has this initial data?
Yes.
Yeah.
Okay. So now, so this is given by C1 is equal to 1 and C2 is equal to 0 in this case. Now, let's take our different family. Let's examine the family given by, let me choose different constants, D1 times e to the 1/2 e to the t plus 1/2 e to the negative t plus D2 times 1/2 e to the t minus 1/2 e to the negative t. This is like my different basis, right? What are D1 and D2 such that y is equal to e to the t? Why don't you try to find the D1 and the D2 such that D1 times this thing plus D2 times this thing is equal to e to the t?
Are they both 1?
Yeah, exactly. Here, D1 is equal to 1 and D2 is equal to 1 will yield D1 cosh t plus D2 sinh t is equal to e to the t. So I still have a unique solution to the differential equation satisfying this initial data. It's still just e to the t. But the point is, if I start off with this way of writing my family, then this particular solution is given by coefficients C1 is equal to 1, C2 is equal to 0. If I start off with this way of writing the general solution, or this way of writing the family, then I get this unique solution to this differential equation and initial data by different coefficients, namely a coefficient of 1 and then a second coefficient of 1. So these are different ways of writing the family. Does this make sense?
Yeah.
Okay, so the point, there are many ways of writing the general solution. Or in other words, there are many fundamental systems of equation, fundamental systems. That is, for this differential equation, one fundamental system is e to the t, e to the negative t, and another different fundamental system is cosh of t, sinh of t. Is that clear? Any questions? No questions at all? This is totally fine?
Yeah, makes sense.
Okay, cool. Yes, so where do we go next after this? Let's do the following. So there are two more things that we want to discuss in 3.2. So two more topics. 3.2 is a very large section. So this topic is just a short theorem, which will be mostly useful for 3.3. So I could discuss it there, but that's going to come up in a couple minutes anyway, so let's discuss it right now. So theorem 3.2.6 is going to essentially be another form of the linearity of solutions. So consider some differential equation, L of y is equal to y double prime plus p of t y prime plus q of t y is equal to 0. Okay? For p and t continuous, or p and q continuous. So here's the claim. If y is equal to u of t plus I v of t, so now we're starting to get our toes into complex solutions. So if y is equal to u of t plus I v of t is a complex valued solution, then u of t and v of t separately are themselves solutions. So the other way is kind of obvious, right? We know from our earlier theorem, namely the theorem of superposition, that if u is a solution and v is a solution to a second order linear homogeneous ordinary differential equation, then certainly I is just a constant, so I vt is certainly a solution, and summing solutions is also a solution. So we know u of t plus I v of t has to be a solution. This theorem allows us to say that in this special case where we have a linear function or a linear combination given by u of t plus I v of t, we can actually go the other way. Does it make sense what I'm kind of claiming here, or what I'm talking about?
Not really,
Not
if I'm
really.
being honest.
Yeah, okay. So let's recall what the principle of superposition is. Principle of superposition says the following. Can someone remind me what the principle of superposition is? Or solutions form a vector space.
Is it if y1 and y2 are a solution, then if you add them up together, it's also a solution?
Yes, it's even slightly more general than that. If y1 and y2 are solutions to a second order linear homogeneous ODE, then so is C1y1 plus C2y2 for arbitrary C1 and C2. So we have essentially been using this the whole time because I've been writing families in this way. I get my hands on two solutions, y1 and y2, and then so long as their Wronskian is not 0, I have an infinite family of solutions given by all of these, right? Is this okay? Do we remember the principle of superposition?
Yes.
Okay, and we proved this, right? It wasn't so difficult to prove, it was just separating out variables. So in particular, as a special case, we know that y1 plus I y2 must be a solution. Right? Because it's just one function plus a constant times the other solution. It's exactly of this form, where now I'm allowing my constants to be complex numbers, but they're still just constants. So when I take derivatives, the constants just pull out. Do we agree with this statement?
Yeah.
Okay. Now, the special claim here is that in this special case, where we write a solution as y1 plus I y2, if we have one solution given by y1 of t plus I y2 of t, then we actually we produce two solutions, y1 and separately y2. So usually superposition says, take two functions, I can add them up together. This is a kind of reverse, which says, if we can write one solution in this special form, then we can actually extract from the data of this one solution two different solutions, y1 and y2. And I want to point out that this is special to the data coefficients, C1 being equal to 1 and C2 being equal to I. If I pick arbitrary random numbers, like if I find some solution, which is 3 times one function plus 4 times another function, that doesn't mean that those two functions separately are solutions. But in this special case where C1 is 1 and C2 is I, then from this one solution, I can extract two solutions.
Can you clarify what the line below where it says in particular as a special case?
So the general theorem of superposition is if you start with two solutions, then all of these expressions are also solutions, right? And down here, I said, in particular, as a special case, y1 plus I y2 must be a solution. I'm just choosing C1 to be equal to 1 and C2 to be equal to I.
Okay, thank you.
Right, so all this is principle of superposition. This material is saying, when you have something that can be written in this very special form, when you have one solution which can be written in a complex way like this, then you actually produce two solutions out of it, namely y1 is a solution and y2 is a solution. And we can prove this. So maybe this would go a little better if you all try to prove this. Why don't you try to show, so if y is equal to y1 plus I y2 satisfies, let's make it explicit, y double prime plus p of t y prime plus q of t y is equal to 0, show that y1 and y2 are also solutions. Why don't you give this a shot? So to get us started, we should just plug in y into our differential equation because we know that it's 0, right? So in particular, we know that d squared over dt squared of y1 of t plus I y2 of t plus p of t times d over dt of y1 of t plus I y2 of t plus q of t times y1 of t plus I y2 of t is equal to 0, right? That's what it means for y to be a solution to this differential equation. What can I do from here?
You can separate out the functions.
I can separate out the functions. I can make it so that I've got one function only in terms of real functions, namely y of t's, y1 of t's. And then I can also separate it out so that I have I times stuff only involving real functions. So in particular, this whole thing turns into y1 double prime of t plus p of t y1 prime of t plus q of t times y1 of t. All this stuff, this is like the real part of the function. And now, plus I'm grouping all my I terms together, I times y2 double prime of t plus p of t y2 prime of t plus q of t y2 of t. I know that this whole thing has to be 0, right? I've just separated things out. So I've got all the stuff that doesn't have a coefficient of I out here. and all the stuff that does have a coefficient of I over here. Are we comfortable with what I've done in these steps, going from here to here?
Yes.
Yes.
Okay. What are the conditions such that a complex number is 0? If I write a number a plus bi, and then I say that is 0, what is a and what is b?
0.
0 and 0. If a complex number, and for any t, this is some complex number, and it's always equal to 0, that means the real part has to be 0, and the complex part has to be 0. So I know this is 0 on its own, and this is 0 on its own. But what does this being 0 on its own mean?
Y1's a solution.
Y1 is a solution. What does this being 0 on its own mean?
Y2 is a solution.
Y2 is a solution. Exactly. So now we see if y of this shape is a solution, then each of these pieces must also be a solution. Notice that if I just put some number here that wasn't imaginary, like if I put 5 here, then one number plus 5 times another number being 0 doesn't mean both of these are 0. It's only because I and 1 are like essentially orthogonal that this works out, if that makes sense. Is this clear? Or are there any further questions?
No, that makes sense.
Okay, great. So we're going to be using this a lot in the next section, because the next section we're going to return to the characteristic equation setting, but we're going to look at the case when the roots are complex. And then what this essentially tells us is that if we have a complex root, then we can take the real part of that complex root, and we can take the imaginary part of that complex root and get 2 solutions very nicely. So we'll see that shortly. Okay. There's one last topic that I want to cover in 3.2 before we move on. How are we doing on time? Oh my. Okay. Last topic in 3.2 is Abel's theorem. And so let me write out as follows. Theorem. And what this theorem essentially tells us is that the Wronskian is some data that's associated with the linear equation itself. Like thus far, we've been taking 2 solutions and computing their Wronskian. But what Abel's theorem is about to tell us is that actually, in a certain sense, the Wronskian is independent of the solutions, and it's something that you should really associate to the differential equation. So Abel's theorem, the theorem is as follows. Yes, here we go. If y1 and y2 are solutions to the second order linear ODE, homogeneous ODE, L of y is equal to 0, and assume that P and Q are continuous on some interval I, then we can compute the Wronskian of y1, y2 of t explicitly in a certain sense as follows. The Wronskian, w of y1 and y2 of t, is equal to c of the exponential, I'll just write it as exp, of negative antiderivative of p of t dt. Okay, so this theorem, as written, should be pretty surprising. What this theorem is telling us is that, sure, on one hand, it is true that the Wronskian depends on the functions y1 and y2, because if you pick different y1s and y2s, then it'll give you different answers. However, the general form of the Wronskian is some function that's explicitly figured out, and then changing the basis, so to speak, changing your two solutions is really only changing the constant in front of this term. So somehow the Wronskian you can figure out up to a constant factor without actually ever finding solutions. So notice that, oh, and moreover, the function, moreover, c of y1 and y2. So c is, if you change around your fundamental system or your two solutions, if you change these around, you will change the Wronskian, but you're only changing this constant out front. And moreover, this constant, which does depend on y1 and y2, doesn't depend on t. So the fundamental idea here is that the Wronskian is actually measuring something a little deeper than just the chosen solutions, because all of the Wronskians associated to a given differential equation will have the same form. Any questions on this, just for what's written? No? Okay, so let's just sketch the proof of this a little bit. So let's write out our two solutions. Since y1 and y2 are two solutions, we can write out y1 double prime plus p of t y1 prime plus q of t y1 is equal to 0, right? Moreover, we can do the same thing for y2. y2 double prime plus p of t y2 prime plus q of t y2 is also equal to 0. Thus far, everyone is fine with what I'm doing, right? Are there any questions about what's going on here? Okay. So what we can do is we can make an algebraic manipulation. We can multiply the first equation by negative y2, and then we can multiply the second equation by y1, and then add. Okay. So at this point, this is just an algebraic manipulation that I'm doing. So I'm saying I'm going to examine the following thing. If these two things must be 0, then y1 double prime times negative y2 plus p of t y1 prime times negative y2 plus q of t y1 negative y2 plus y2 double prime times y1 plus p of t y2 prime y1 plus q of t, y2, y1, all this must be equal to 0. These two things are equal to 0. I multiply this by something, it'll still be 0. I multiply this by something, it'll still be 0. Then I add those two things together, and I'll still get something that's 0. Okay. Does anything cancel in this big unwieldy equation?
Give me just a second.
Yeah, sure. It's kind of big.
It'd be the q of t, y1, y2, because one of those.
Exactly. Absolutely. These two things will cancel. I have a q of t y1 times negative y2, and I have a plus a qt y2 y1. These things will certainly cancel. So what I get in the end, and I'll rewrite this as follows, y1 double prime, or yeah, let me start with this one. Y2 double prime, y1 minus y1 double prime y2 plus p of t, and now here I've got p of t y2 prime y1 minus y1 prime y2. All this is going to be equal to 0. Are we okay with what I've done here?
Yes.
Okay. Now, for an interesting question, can anyone recognize what this kind of looks like?
Product rule? Or
This
equation rule?
looks like a product rule, exactly. This looks like a product rule if I make a new function, w of t is equal to y2 prime y1 minus y1 prime y2. Right? Now this thing looks like y prime, right? If I take derivatives here, I'm going to get y2 double prime plus y2 prime y1 prime minus y1 double prime y2 minus y1 prime y2 prime. I'm going to have cancellation. I'm going to get this. So this looks like w prime of t plus p of t w of t equaling 0. Are we okay with this?
Yes.
Excellent. How do we solve, and okay, this is now a different auxiliary differential equation. What is the order of this differential equation?
Is that just a first order now?
This is a first order. Is it linear?
Yes.
Yeah, it's linear in W. Differential equation, ODE. How do we solve these?
Integrating factor?
Solve these by integrating factors. Okay. So what we're going to get,
To the bottom of that page real quick for 1 second.
oh, yes. Okay, there's another thing that I want to bring up. Why did I call this W? Why did I give this name W? It's supposed to be suggestive.
Is it gonna have something to do with the Wronskian thing?
Absolutely. This is precisely the Wronskian of the pair of solutions y1 and y2. This right here, this expression, is the same as the det of y1, y1, y1 prime, y2, y2 prime, right? Or the negative of the determinant, but it's essentially the determinant, right? So the things that Abel has done in this beautiful idea is he has taken two different solutions to a second order linear differential equation. What he has done is he's done some algebraic manipulations until he was able to get this new expression, which he recognized as a differential equation, first order linear, where the thing that we were trying to find is the Wronskian of the two original functions. So this thing right here is telling us that there's some differential equation that the Wronskian has to solve, and we're going to solve it using an integrating factor, which only remembers the P of t business. Okay? So in the end, if you trace through, so now solve this first order linear system for W, and what you'll get is that W of t, which is now the solution to that differential equation and also the Wronskian for a different differential equation and pair of solutions, is equal to some constant times e to the negative antiderivative of P of t dt, which is what we wanted to prove. So this is exactly what we get by solving for this function using our integrating factor methods. And you can check precisely that if you take the derivative of this function, then you will get the solution to the differential equation that we wrote down. Okay, so this is Abel's theorem. And what it allows us to do is it allows us to compute Wronskians even if we don't have solutions, although we can only compute them up to a multiplicative factor. So let's quickly do an exercise before we, man, it's already 20 minutes left. Let's do an exercise.
Why would we want to compute a Wronskian before we have solutions?
Maybe we should interpret this in the following way. What this means is that the Wronskian is an additional interesting piece of data that you can gain from a differential equation that is in a certain way kind of independent of your family of solutions that you might eventually be able to find. And here's another critical point, is that in general, solutions to second order differential equations may be essentially impossible to find. We haven't really bumped up against that at this point, but if you take a general second order linear that looks like y double prime plus p of t y prime plus q of ty being equal to 0, if p of t and q of t are some strange enough functions, then you might not ever actually be able to get explicit solutions. But the Wronskian satisfies a first-order linear differential equation, and those we can always find explicit solutions to, namely they're of this form. So it's true that it seems a little bit backwards to compute the Wronskian before computing solutions, because thus far we've only seen easy differential equations where we can actually get solutions. But there are plenty of cases when you can't get explicit solutions, but you could compute the Wronskian. Does that help?
Yeah.
Okay. So for instance, compute the Wronskian without solving for t squared y double prime minus t times t plus 2 y prime plus t plus 2 y is equal to 0. And notice the only second order linear differential equations that we have any inkling of how to solve are those where all the coefficients are constants. A priori, at this point, you have no idea how to get solutions to this differential equation. But you can still compute the Wronskian right away. Up to a constant factor. So what's the first thing that we should do here?
Get it in the form we want.
Get it in the form we want, which means dividing everywhere by t squared. So here we can write this as y double prime minus t plus 2 over t y prime plus t plus 2 over t squared, y being equal to 0. And then Abel's theorem just tells us what to do, right? Wronskian w of t is equal to a constant multiple of e to the negative antiderivative negative t plus 2 over t. What's the antiderivative? And we can pull this negative out. So what's the antiderivative of t plus 2 over t?
T plus 2 ln t.
Yeah, so c, this is going to be e to the t plus 2 natural log of absolute value of t plus some constant c1. But what I'm going to do is I'm going to split this up. First of all, e to a constant doesn't matter because I've already got some arbitrary constant that I don't know out here. So I'm just going to write this as c e to the t. Then I'll write this as e to the natural log of t squared. Right? I can move constants into the exponents via my rules of log, or natural log. So in the end, I get c t squared e to the t as the Wronskian. You don't know the actual Wronskian for any pair of solutions because we didn't find any pair of solutions. But by the existence and uniqueness theorem, we know that solutions exist as long as you're away from t is equal to 0. And whatever the Wronskian of those two solutions, whatever they might be, it will be equal to some constant times t squared times e to the t. Any questions on this? Okay, so I'm going to interpret your no questions as not really that everyone is perfectly happy, but more that this chapter had a ton of material and we haven't done enough exercises and it's still not shaking out quite enough, because that's how I remember feeling when I covered this material the first time. So the fortunate thing is that we're going to spend the rest of this chapter doing explicit computations where we kind of see all of this machinery in action. So that's the positive side. We've got 13 minutes left. So what I should do is I should give us a summary and then do the very beginning of 3.3. Before I do that, though, are there any questions? I'm asking you. Okay, let me give a little summary of all the material that we saw in 3.2. First of all, we have existence and uniqueness theorem for solutions to IVPs for second order linear. And there are some conditions that you should remember here. For instance, you have existence and uniqueness on intervals containing the initial data such that P of t is continuous and Q of t is continuous and G of t is continuous. Remember, I don't need to assume homogeneous for existence and uniqueness. Okay, this is one point. Another point is that we expect two-dimensional families. Expect two-dimensional families of solutions, depending on some constants C1 and C2. Another point is that two solutions, or if we have two solutions, linear combinations, that is C1 Y1 plus C2 Y2, will give all solutions if the Wronskian W of Y1, Y2 is not the zero function. And lastly, the Wronskian may be computed using Abel's theorem.
Can you move the paper up a bit, please?
Oh, yep. Here are some important points that I would like for you to remember or try to digest coming from this kind of big convoluted chapter or section. Okay. If we have all this information, then in the last 10 minutes, I'd like to just get started on section 3.3, which is a return to stuff that's more computational and more explicit.
I have a quick question.
Yeah, absolutely.
So we would need the solutions to find the actual value of C for when we use.
That's correct. You can't completely determine the Wronskian as a function without solutions, but you can tell what the Wronskian is up to some constant. That's right.
So, but we can't decisively say that it's not 0.
That's correct. If you pick two solutions which are not linearly independent in the correct way, then that C could be 0. That's correct.
Okay.
Could you also clarify? I'm sorry, Julia, I'm still a little confused. Where you say Wronskian may be computed up to scalar, what do you mean by that?
What I mean is the following. In this particular differential equation up here, I've got no idea what the solutions look like, right? We simply don't know what the solutions look like. But I do know that there must be solutions by the existence and uniqueness theorem. So let's say that there are solutions y1 and y2 that satisfy some initial data. I don't know what it is. There must be solutions. When I compute their Wronskian, w of y1 and y2, it has to look like this function. I can never get a cosine of t appearing in the Wronskian. I can never get a t cubed appearing in the Wronskian. I can never have a natural log of t appearing in the Wronskian. The only possible Wronskians associated to this differential equation are some constant number times t squared times e to the t.
But that's dependent on each.
Yes, it depends on y1 and y2. And if I take the Wronskian, let's say that there's some Wronskian here, such that w of y1, y2 is equal to t squared e to the t, it's very possible that I can take a w and a y1 and a y2 prime, some different solution, such that these two are still a fundamental set, and now the Wronskian would be like pi t squared e to the t. Like, you'd be able to find solutions, probably not find them explicitly, but what this theorem is telling you, essentially, is that, what this theorem is telling you is that for any two solutions that you can't write explicitly, but you know they have to exist, when you compute their Wronskian, which you can't do explicitly because you don't have the actual functions, but you know it'll look like some constant times t squared e to the t.
Okay, thank you.
Any further questions on this material? Yeah, maybe what Abel's theorem should be interpreted as is that the Wronskian is actually more accessible data than the solutions. We started off by saying, if you've got solutions, then you can compute the Wronskian. But it turns out that the Wronskian is easier to compute than solutions in general. This is how you compute it. Up to a scale. And I think here's maybe one further direction where we can see Abel's theorem going, is that maybe someone would try to find equivalence classes of differential equations. Basically, maybe there are families of linear differential equations which more or less act the same. They're just different by a change of basis. Like maybe if I rewrite my functions in terms of t in terms of some change of basis in t, maybe all these differential equations are related to each other by some change of basis in t. The Wronskian might be some computable way of determining when two different differential equations are remarkably different. because it seems to be some sort of invariant of the differential equation. But okay, let's not go down that. Okay, we have like essentially no time actually. I don't want to start a new topic here with 4 minutes to go. So I'm just going to say that's going to be it for today. And I'll see y'all on Monday.
Thank you.
Thank you. Thank you.
Yep. Have a nice afternoon.
Thank you.
You too.
And I'll be here for office hours. If anyone has any questions, I'll be back maybe around 1 or 1:05. So if you have any questions, hang on for a couple minutes. Otherwise, have a nice afternoon and a nice weekend.